What is up, guys? Welcome back to another wonderful episode of Ya Boy's Garage. Today we're going to be diving into replacing a quad array BJT package. It is an SIP10 package, and we're going to be replacing those BJTs with MOSFETs. And instead of just diving into replacing it with MOSFETs, I want to go ahead and dive into datasheets and explain why we're using the MOSFETs and what is going on with these ICs. Hopefully this will give you a better understanding of why I chose the components I did and why they're a better fit for this component replacement. So this is the component we're working with today. This is the STA413A. This is the IC located at QM3 and OBD1 Honda ECUs. It is a quad array driver featuring BJTs, and as you can see here at the top of the screen, they have a built-in avalanche diode. We can see they're NPNs, meaning they're a low side switch. We can see over here they're a 10-pin package in this case. We have an example drawing down here, which is really cool because it shows people how to sketch out this exact IC. And then we have these ratings right here. And so I figured that even though the data sheet kind of gives us an example of what we're doing, it tells us it's an NPN switch, and it tells us it has an avalanche diode, why not dive into what the data sheet says, what it means, and how we choose our replacement components. So this is our VCBO. It is our voltage rating between the collector and the base when the emitter is not connected. So the collector is essentially our input, the emitter is our output, and the base is basically what turns the device on to allow the collector to flow through to the emitter. It's letting us know that when the emitter is not connected, meaning the load is not hooked up to the device. Let's say in this case the load is a solenoid. If that solenoid was not connected or was disconnected, it would mean that between the incoming source, which is on the collector, and the base itself, which is the signal that turns it on, we want no more than roughly 35 volts plus or minus. Okay, there's a 5 volt tolerance there, and we're just going to roll with 35 volts as the number for the VCBO. The VCEO is between the collector and the emitter when the base is open or disconnected. So it's actually the same voltage tolerance, and it's just saying that when the base isn't present, this is the maximum voltage that can be present between the input and the output of this transistor. The VEBO is actually the max between the emitter and the base when the collector is not connected. In other words, this is a reverse current situation, and it's letting us know that we have a 6 volt tolerance. The IC is the maximum amount of current the collector can handle without overheating. In this case, the IC can handle up to 3 amps of current. IB is the maximum amount of current that the base can handle without overheating. BJTs rely on constant current going to the base to make them work, and that is why there is a current reference on here, not a voltage reference. This is PT. This is the overall power dissipation, and it lets us see it at 2 different ratings. We have the 25 Celsius, which is about a little over room temperature, and then we have the absolute maximum heat rating, which is 150 Celsius, and you can see that we have a 4 watt dissipation at room temperature, and we have a 20 watt dissipation at much higher temperatures. TJ is actually the maximum temperature that the device can operate at, which is 150 Celsius. T-stage or TSTG is the storage temperature, meaning this is the device's minimum and maximum temperatures that it should be stored at. So we're looking at a minus 40 condition to a 150 Celsius condition is the storage temperature of the device. The ICBO is the leakage from the collector to the base when the device is off. You can see here we have 10 UA. The IEBO is the leakage from the emitter to the base. Again, you can see we have 10 UA. This is the VCEO. It is the maximum voltage between the collector and the emitter when the base is open. Very similar to what we mentioned earlier in the very beginning, the VCBO. We're looking at a range of between 30 to 40 volts. HFE is how much the collector is amplified compared to the base. And VCE or SAT is actually what the collector emitter on the BJT is at full tilt. So this is kind of where we determine what it can handle. Here you see we have a rating of 0.5 volt at 1 amps at room temperature. Okay, so we've kind of briefed on what the specifications are for this device. We've briefed on a little bit about what those specifications mean. So now let's kind of dive into the replacement component I chose and why I chose that component. So this is the replacement. It's an Infineon MOSFET. It is the BSZ series, and this is a low side switch. It works just like a regular NPN, and being that it is going to switch on the low side of the circuit. Right off the bat on this table, we see we have the VDS, which is at about 60 volts. This is comparable to the VCBO of the BJT, which was 35 volts, so we have nearly twice the headroom on what this device can handle. Scrolling on down here through this. So the VEBO, or the essentially the base reverse polarity situation there, we had about 6 volts. We can compare that to the gate source voltage, and we see that's actually around 20 volts. So we have 3 times the threshold tolerance here of what the device can handle in a reverse polarity condition. We can also have up to 20 volts on the gate without the MOSFET bitching at us. So the MOSFET has a much higher voltage rating than the original device did for the gate. It's hard to compare the gate to the base because they're doing different things. A gate is driven by voltage and a base is driven by current, but this is the closest we can get to comparing those values. So the IC rating on the BJT was 3 amps. If we look over here on ours, we see that there's a couple different numbers here going on for the continuous drain current. The continuous drain current is the closest thing we're going to get to that IC rating. And we can also see there's a temperature reference off to the side. If we focus at room temperature, we actually have a 98 amp rating, but you'll notice it says TC, and down below we see TA. TC is the cooling factor when it is clamped to a heatsink or the case, and TA is when it is being air cooled. So we're going to focus on TA since TA is actually in closer alignment to the original BJT that we're comparing it to, which is 17 amps. So 3 amps versus 17 amps. So this device has a much higher threshold on the continuous drain current than the BJT. Once again, we have way more headroom and or efficiency with using a MOSFET. So if we look over here at power dissipation, you'll see once again off to the side, we have a TC value and a TA value. The TA value is what we're going to go with, which is an air-cooled setup. Even though I put some nice copper pores on my PCB, we're going with just a regular air-cooled setup with no sort of clamping or base or case against the device. The BJT was rated around 4 watts of heat dissipation, and we're actually at 2.1 watts of heat dissipation. So we have almost 100% improvement in efficiency over the BJT in power dissipation, which means it operates way cooler. Down here, looking at the operating storage temperature, you can actually see the device can not only operate, but can be stored at 15 degrees Celsius cooler than the BJT. So it has the same maximum heat range at 150 Celsius, but it can actually stand up to a harsher cool environment of minus 55 Celsius. Well, we're not going to really see something like that in an automotive application. It still shows the device has much larger headroom than the original BJT. So the ICBO of the BJT was around 10 UA, and if we look here on our MOSFET, the closest we can get to that is with 0 gate voltage drain current. And you'll see that it's actually at 0.5 UA, and that's at the same ambient temperature, which means that the MOSFET is 20 times as efficient than the BJT. The IEBO of the BJT was also at 10 UA, and if we look here, the closest we're going to get to that is gate source leakage current. And in our device, under the same ambient temperature, we're looking at 10 NA, which is about 1,000 times the efficiency of the BJT. Crazy, right? We're talking 1000% less leakage than a BJT. The VCEO of the BJT was around 30 volts, and that compares back to what we were talking about at the beginning with the MOSFET at 60 volts. So once again, we have twice the headroom on the MOSFET than we did with the BJT. I'm going to go back up here to the RDS on. So the RDS on has 4.2 milliohms. If we multiply that times the amps, which is 1 amp, that puts us at 0.0042 volts. The BJT had a VCE value of 0.5 volts. So compare 0.5 to 0.0042. There is a tremendous difference there in efficiency. So we're talking the MOSFET that I've chosen is extremely cooler in operation than the BJT. It is way more efficient than the BJT. It has almost a non-existent amount of leakage compared to the BJT, and it has twice the capacity and headroom over the BJT. So the MOSFET that I've chosen is extremely robust. It is great for an automotive application, and I know you keep hearing the number 60 volts. You need to think of things like load dumping, which is where the battery is disconnected while the alternator is still charging. There's a momentary brief spike in the voltage that happens in the car. You also need to think of inductive loads, such as when a relay kicks on or off for the cooling fan. Those things cause spikes in voltage, and this is the exact reason why having a 60 volt rated MOSFET is better than having the original device of the BJT, which was rated at 30 volts. While we don't typically see spikes like this in automotive application, you should understand that QM3 has failed several times under stock conditions in these cars, which means those spikes have occurred and killed the BJT. So this replacement is not only just a drop-in for what was there, it is actually an improvement over the IC that was there. Now that we've looked at the data sheets together, let's go ahead and jump over to schematics real quick and take a peek at those. So here's the schematics that I've drawn up for the QM3 replacement. You can see here I've given my part numbers for the MOSFET itself. I've given the resistor values as well as my Zener clamping diode. So D1, D2, D3, and D4 are Zener diodes, and they're actually set in place between the gate and the source. And the reason for that is we don't want the gate to exceed 20 volts. If you remember looking at the specification sheet we were just looking at, the data sheet, it said that the gate value was at 20 volts. So I've put a Zener on there that is rated at, I believe, 12 volts. So if there are spikes, transients like that, we're actually not going to exceed 12 volts going into the gate. With the ECU right now, we are providing a 5 volt signal to turn the gates on and off. So we're likely never to see above 5 volts, but if there was spikes, this Zener being in place will protect the device from being anywhere close to the threshold it can tolerate. R2, R4, R6, and R8 are a high resistance. They're a 46 or 47,000 ohm resistor, and that is to pull the gate of the MOSFET to ground, meaning it keeps the MOSFET in an off condition when there's nothing happening from the gate source. The gate comes from each of the 4 points of the ECU, identified as gate 1, 2, 3, and 4 for the inputs. The resistor that the gate is plugged into is a 47 ohm resistor, and I went with that resistor because a low ohm resistor like that actually helps to reduce ringing and spikes from entering the gate. It just helps to smooth the signal. So when ringing occurs, it's basically high oscillations. It's kind of like this zigzag effect that comes on in the signaling. And when it goes through that resistor, it kind of turns it into more of a sine wave going through, like AC. So it helps to smooth the signal, which prevents it from doing a frequent on-off scenario. So that's what's going on there with the resistors and everything. So it's a super simple schematic, as you can see here. There's 4 of these guys. They're all laid out. There's a 10-pin header at the very bottom, and everything is pinned out and flagged accordingly. So yeah, I hope you guys enjoyed the video. This was just a technical side showing why I chose MOSFETs over BJTs and kind of diving into the data sheet side, getting a little more technical with you. The soldering and the installation of the part, I'm going to go ahead and throw in a different video. But for now, I hope you guys enjoyed the content. Hopefully you found some things to nitpick or call out about the content. Please feel free to drop it in the comments, like, subscribe, and as always, I will see you in the next one, and I swear the emulator is coming. Hang tight.